So today we're going to be providing a run through of Chem 100 Laboratory 5, which focuses on compounds and their bonds. So first and foremost, I'd like to direct your attention to the fact that in order to find this lab and all of the associated materials, we're going to go to the Laboratory 5 module in Canvas. First, I'd like to direct your attention to the Laboratory 5 overview page, which talks a little bit about the learning objectives for this laboratory, along with some recommended reading. Next, there is the Laboratory 5 procedure and report sheets, which are found in the section titled Chem 100 Laboratory 5 Procedure and Report Sheets. So here are what the procedure and report sheets look like for Lab 5. You're going to want to make sure to download and print these report sheets or transport these report sheets to a digital note-taking program such as OneNote. Whatever is most convenient for you, you can do it in hard copy or digital formats. Both are fine. Next, and most importantly, is the Laboratory 5 Canvas page, which looks like this. For Laboratory 5 in particular, I strongly recommend that you read the pre-lab reading in detail, as it provides a lot of background information along with examples in terms of how to complete each part of the lab, in terms of writing electron configurations, naming compounds, and drawing Lewis structures. And this whole introduction section is divided in different parts with multiple step-by-step examples in order to solve all of the problems that you'll encounter as part of this laboratory activity. Additionally, this Laboratory 5 page also contains any of the photos and videos that we'll be referencing in order to complete the lab report sheets. So I would encourage you to read the introduction section on your own time, but also you need to have the Laboratory 5 Canvas page open, as we'll be referencing it and using it to complete our lab report. I'd also like to draw your attention to the pre-lab lecture, which contains a lot of useful background information in order to complete your lab report in an effective and efficient manner. Finally, this recording, which provides a full run-through of Laboratory 5, is found in the page titled Experiment 5 Laboratory Recordings, Video Walkthrough to Complete Experiment 5 Virtual Laboratory. So this is the recording that you're watching right now. Finally, once we complete all of our report sheets, you'll be turning in all of your report sheets into the section titled Laboratory 5 Report, Compounds and Their Bonds. Okay, so now that we have that introduction out of the way, here is the full set of report sheets that we'll be filling out. So let me import the report sheets into my structure drawing program. Here we go. So here are the full set of report sheets, and we're going to be filling them out and working through this together. Okay, so first and foremost, in the procedure and report sheet pages, we have a little pre-lab checklist. So we need to open up the laboratory page in Canvas. You're going to want to read the background reading in the lab Canvas page. You're going to want to watch the pre-lab lecture. And if you have the procedure and report sheets and you want to reference back to this video, you can open up the lab page titled Experiment 5 Lab Recordings, Video Walkthrough to Complete Experiment 5 Virtual Laboratory, which is the video that you're watching right now. As always, if you're asked to view a video or photo in Canvas, all videos for this experiment are found in the Canvas page for Laboratory 5, Compounds and Their Bonds. Okay, so let's work through the procedure. So in the first part of this lab, we're asked to complete the following table. So in this case, you're given an element name. You have to write the atomic number, the electron configuration, the Lewis dot symbol, and predict how that given atom will ionize. For example, potassium, as it's a metal, prefers to lose electrons equal to its group number to reach an electron configuration matching the closest noble gas. So potassium, as it's a 1A element, prefers to lose one electron and adopt a configuration of argon. When it loses one electron, generally metals form ions with a charge equal to the group number. Since it's a 1A element, we'd predict an ion charge of +1 for potassium, which would be potassium plus, which is named as the potassium cation. Let's do another example. You're going to want to have your periodic table for all of this. So we're going to pull open our copy of the periodic table. And let's take a look at phosphorus. So phosphorus is a 5A element with an atomic number of 15. Phosphorus has an abbreviated electron configuration of neon 3s2, 3p3. In terms of its dot symbol, as it's a 5A element, it has 5 valence electrons. So we'd place 1, 2, 3, 4, 5 dots around phosphorus. Generally, for nonmetals, they prefer to adopt a charge equal to the group number -8 or -3. In order to reach a noble gas configuration of 8 valence electrons, phosphorus needs to gain 3 electrons. So phosphorus as a nonmetal prefers to gain 3 electrons to reach a noble gas configuration. This gives us a noble gas configuration of argon, and this gives a predicted ion charge of -3, giving us phosphorus 3-. One thing that's important to note is that when you're dealing with anions, you have to rename the anion with the IDE suffix. So instead of phosphorus, this would be phosphide. Okay, with these two examples in mind, you're going to complete the remainder of this table where you're identifying the electron configuration of each atom, predicting how that atom will ionize, and in turn, writing the electron configuration, symbol, and name for that cation or anion that's formed during ionization. So you'll complete the remainder of this table independently. Let's take a look at the next part. So part B, ionic compounds and formulas. So in Canvas, you're provided images and physical property data such as density and melting point for a sample of sodium chloride. We're going to record our observations for the appearance of the sodium chloride sample and record the density and melting point. Okay, so here's the sodium chloride sample. This looks like a white solid. The density is 2.16 gram per mil. The melting point is 801 degrees Celsius. Let me just make sure I have the density written down correctly. Okay. And the melting point is 801 degrees Celsius. One thing that we're noticing almost immediately, ionic compounds have very, very, very large melting points. It takes very high temperatures to melt an ionic compound. The next activity that we're working on is completing the following table, where we're given the name of an ionic compound. We're asked to write the cation and the anion and the formula. So we have one example for sodium chloride. Sodium is sodium plus, chloride is Cl minus, and that gives us a formula of NaCl. Let's do another example, aluminum sulfide. So aluminum is a 3A element. It's a metal, so it prefers to adopt a charge equal to the group number. Sulfide, sulfurous, is a 6A element. Sulfur prefers to adopt a charge equal to the group number, which is 6 minus 8, which is minus 2, which gives us sulfur 2 minus. The key method that we use to write the formula of ionic compounds is you cross the charge into the corresponding subscript. So for example, this 3 on top of aluminum ends up in the subscript for sulfur. This 2 minus on sulfur ends up in the subscript for aluminum. This gives us Al2S3. The reason why this works is this ensures that the charges are balanced. The two 3 plus charges of aluminum are matched by the 3 2 minus charges of sulfur, giving us a net total charge of 0. So for example, in aluminum sulfide, we have aluminum 3 plus, S2 minus, and the formula Al2S3. With this example in mind, I'd like you to complete the rest of this table independently. Let's keep going now. We're next asked to complete this next table where we are given the formula. We're asked to identify the cation and anion and then name our compound. So in this case, for lithium oxide, just to show the process, we can in turn get back to the cation and anion by moving the subscript back to the charge. This gives us lithium plus, which matches the expected +1 charge for a 1A element, and O2 minus, which matches the predicted -2 charge for a 6A element anion. To name these kinds of binary ionic compounds, you name the cation, then you name the anion, replacing the ending with IDE. Let's do another example. For MgCl, so magnesium is a 2A element, so we predict it to have a 2 plus charge. Chloride is a 7A element. 7 minus 8 gives us a -1 predicted charge, which would be Cl minus. We name the cation, which is magnesium. Then we name the anion, which is chloride. So this would be magnesium. Instead of chlorine, it's magnesium chloride. Wonderful. With this example, I'd like you to complete the remaining problems in this table independently. Let's take a look at this next part of the procedure. In this case, we're dealing with metals and ionic compounds with variable charge, or transition metal ionic compounds. So in Canvas, we're provided images and physical property data such as density and melting point for a sample of iron 3 chloride with a formula FeCl3. We're going to record our observations for the appearance of the iron 3 chloride using the image provided in Canvas, and we're going to record the density and melting point using the data provided in Canvas. So we'll go to part C. Here's the image of iron 3 chloride, which is a yellow solid, and we have the density and melting point. So let's just write that down. For iron 3 chloride, one moment. Okay, so in terms of appearance, we have a yellow solid. In terms of the density, we have a density of 2.90 gram per milliliter. And in terms of a melting point, we have a melting point of 306 degrees Celsius. So again, as expected for an ionic compound, its melting point is quite large. Okay, let's keep going now. We're now asked to complete the following table where we have to identify the cation and anion and their charges and the formula for each of these following transition metal ionic compounds. Now, Just like before, we're going to figure out the charge of each component ion by, for example, for iron 3 chloride, we have a formula of FeCl3. We cross the subscript into the corresponding ion's charge. That gives us a predicted charge of Fe3 plus and Cl minus. Now, transition metals can have variable charge, and the exact charge of the transition metal is not just indicated by the formula, it's also noted in the name. So for iron 3 chloride, this 3 tells us we're dealing with iron 3 plus. So let's do another example here. For cobalt 2 oxide, this 2 tells us we have cobalt 2 plus. Oxide tells us we have oxygen, which has a 6A element. Oxygen prefers to adopt a 2 minus charge, because remember 6 minus 8 gives us negative 2. Now that we have cobalt 2 plus and O2 minus, we can cross our charges into the subscript, and that gives us CO2, so cobalt 2O2. As a last step, we want the simplest ratio. So this 2 to 2 ratio simplifies to 1 to 1, and that gives us a formula of COO for cobalt oxide. So again, you write out each ion, you write their charges, you cross the charge into the subscript, and then you simplify this ratio of atoms to the simplest whole number ratio, which means no fractions, no decimals. So with this example in mind, I'd like you to complete the remaining problems in this table independently. Let's look at another example. So here we're asked to complete the following table. This time we're given the formula and we're asked to write the name for this transition metal containing ionic compound. So looking at Cu2O, in order to name a transition metal containing ionic compound, you're going to first have to figure out the charge of the transition metal. So we write out our formula, we cross the subscript back into the charge, that gives us copper plus and O2 minus. As an additional check, you make sure that the charge for your main group element matches the predicted charge. And the 6A element, like oxygen, does in fact have a 2 minus charge, which tells us this copper has a +1 charge. So we name this as copper 1. This 1 tells us copper has a +1 charge, and then we name our anion, which is oxygen. Instead of writing it as copper oxygen, we change our suffix to IDE. So instead of oxygen, this would be copper 1 oxide. Let's do another example. CO2S3. So we take our subscript, we cross it into the corresponding atom's charge. That gives us cobalt 3 plus and sulfur 2 minus. A 6A element does have a predicted charge of 2 minus, so we're good to go. That tells us this cobalt has a 3 plus charge, which means this would be named as cobalt 1, 2, 3, Roman numeral 3 for this 3 plus charge, Roman numeral 3, and then instead of sulfur, this would be sulfide. So we'll name this as cobalt 3 sulfide. One thing that I do want you to be careful of is that for fixed charge transition metals such as silver, silver is known as a fixed charge transition metal. And for elements such as silver and zinc, you do not have to put the charge in the name because silver and zinc have a fixed charge. So for example, for this Ag2O, we have Ag plus and O2 minus, and this would be named just as silver oxide. This difference in naming convention only occurs for fixed charge transition metals like silver and zinc. Now that you have these examples in mind, I'd like you to complete the remainder of this table independently. Let's look at another set of activities we have to complete. Looking at part D, in Canvas, we are provided with the images and physical property data such as density and melting point for a sample of potassium carbonate. This is an ionic compound containing polyatomic ions. We're going to record our observations for the appearance of the potassium carbonate sample, and we're going to record the density and melting point for the potassium carbonate sample using the data provided in Canvas. Okay, so let's do just that. So we're in part D. Here's what potassium carbonate looks like. It is a white solid. Let's record its density now, which is 2.43 gram per mil, and its melting point is 891 Celsius. Let me just make sure I recorded that correctly, and that I did. Okay, wonderful. Now we're asked to complete the following table, where we're given the name of an ionic compound. We are asked to write the cation and anion, and we're also going to need to write the formula. There is a table of polyatomic ions and their names provided both in the chapter notes and the reading. And I would encourage you to have this table available as you complete this exercise. Okay, so let's go about completing this exercise. So in the first example, we have our cation, which is potassium plus. We have our anion, which is carbonate, which is CO3 2 minus. We cross the charge into the subscript, and that gives us K2CO3. This is the full formula for potassium carbonate. Let's look at another example. This time, let's take a look at, for example, cobalt 3 hydroxide. This is an example of a transition metal containing compound that also has a polyatomic ion. From the name, this cobalt 3 tells us we have cobalt 3 plus. Hydroxide is a named polyatomic ion of the formula OH minus. From here, we cross the charge into the corresponding atom's subscript, and that gives us cobalt with 3 hydroxides, or a formula of COOH3. Remember, this subscript applies to the entire polyatomic ion. Very important to keep in mind. So this would be the formula for cobalt 3 hydroxide. With these examples in mind, I'd like you to complete the rest of this table independently before you turn in your report sheets. Let's look at another example. Here we're asked to complete the following table where we're given the formula and we're asked to write the name of an ionic compound that contains a polyatomic ion. So for example, for MgSO4, magnesium is a 2A element, so we'd expect a predicted charge of 2 plus. Sulfate is a named polyatomic ion, SO4 2 minus. So now that we have our cation and anion identified, to name these polyatomic ion containing compounds, you name the cation, which is magnesium, and then you write the name of the polyatomic ion anion, which would be sulfate. So this would be magnesium sulfate. Let's look at another example, AlNO3. So aluminum is a 3A element, so we'd expect a 3 plus charge. You can also get that by crossing the subscript up into the charge. So we have a 3 plus charge for aluminum. Nitrate is NO3 minus. This is a named polyatomic ion. So to name this compound, we write the name of our cation, which is aluminum, and then we write the name of the anion, which would be nitrate. So this in total would be aluminum nitrate. So with that example in mind, I'd like you to complete the remaining problems independently. Let's move on now to part E, which focuses on molecular compounds. So in Canvas, we were provided the images and physical property data, such as density and melting point, for a sample of water, also known as dihydrogen monoxide. So we're going to record our observations for the appearance of water, and we're going to record the density and melting point for the water sample using the data provided. So taking a look at Canvas, here is the image of water. It is a clear liquid, has a density of 0.997 grams per mil, and a melting point of 0 degrees Celsius. One thing that should immediately catch your attention is the fact that water, as it is a covalent compound, generally has a lower melting point than comparable ionic compounds. Ionic compounds have large melting points, covalent compounds have small melting points or low melting point values. Okay, let's talk about the next exercise. So here we're asked to complete the following table, where we're asked to write the formula for each of the covalent compounds. So when you name covalent compounds, you're going to have to be familiar with the common prefixes. So for example, diphosphorus pentoxide, the di tells us we have 2 phosphorus atoms. Pentoxide tells us we have 5 oxygen atoms. Note, for the first element, if there's just one of the first element, you do not include a prefix. So silicon tetrachloride tells us we have 1 silicon atom. Tetra means 4, so that means we have 4 chlorine atoms. So with this example in mind, I'd like you to complete the remaining problems independently. Let's look at the next table. So IBr5. We're asked to name this compound. So first, we write the name of our first element, which would be iodine. Because it's the first element, we don't need to have a prefix if we just have one of the first element. Because there's just one iodine, we name it as iodine. We don't have to do monoiodine or anything of that nature. Next, we look at our second element. In this case, we have 5 bromine atoms, so we use the prefix penta, and then the name of our second element, which would be bromide. For the second element in the covalent compound, you change the suffix to IDE. So this would be named as iodine pentabromide. Let's look at another example. So P2O3, because there are 2 phosphorus atoms, we name this as diphosphorus. Di indicating we have 2. Because we have 3 oxygen atoms, we use the tri prefix. So this would be diphosphorus trioxide. Again, the IDE suffix is applied to the second element in the name. So with this example in mind for naming covalent compounds, I'd like you to complete the remaining examples independently. Okay, last activity for this lab report. So here we're asked to draw some Lewis structures. So the method that I like to use for drawing Lewis structures is I like to count the number of valence electrons, which are equal to the group number for each element. So hydrogen has 1 valence electron as it's a 1a element, and there are 2 hydrogens, so we have 2 from hydrogen. For oxygen, we have 6 valence electrons, and there's 1 oxygen atom, and we add up our total. We have 8 valence electrons to work with. We put the least electronegative non-hydrogen atom, which in this case is oxygen, in the center, and we surround it with our 2 hydrogen atoms. We then form 1 bond each. That gives us 4 electrons remaining. Each of these bonds are 2 electrons, so we subtract 2 4 electrons from our total. We then place lone pairs on the most electronegative atoms on the outside first. Because oxygen is the only atom that doesn't have a complete octet, we place our remaining 4 valence electrons on oxygen to fulfill its octet. Oxygen, and most non-hydrogen elements for that matter, want 8 total bonding and valence electrons. As we can see, 2, 4, 6, 8. Hydrogen only wants 2 valence electrons, which is accounted for here by the fact that each hydrogen has 1 bond to oxygen. Each hydrogen has 2 electrons to its name. So we fulfilled the octet rule on all of our elements, so we are good to go. Now, in terms of electron groups, you're going to take a look at the central atom here, and you're going to note how many bonded atoms or lone pairs we have in total. So I have 1, 2, 3, 4 electron groups, and how many lone pairs? 1, 2 lone pairs. You're then going to reference the table in Canvas, which has all of the electron pair and molecular geometries. So we have 4 electron groups and 2 lone pairs. This gives us the bent molecular geometry. So we're going to write that down. Now, in terms of whether or not an element is, or whether or not a molecule is polar, there are 2 rules for polarity. The first of which is the central atom bonded to different atoms. If that happens, there's going to be an imbalance in bond polarity in most cases, so the molecule will be polar. The second thing we have to look at is, do we have polar bonds? And yes, we do. These oxygen-hydrogen bonds have a difference in electronegativity. And because this central oxygen atom has an asymmetrical geometry, because this central oxygen atom has a lone pair, this geometry is bent, these bond dipoles don't cancel. And there's a net molecular dipole, which makes this molecule polar. As a general rule of thumb, if you see a lone pair on your central atom and there are polar bonds in your molecule, your overall molecule will be polar. Okay, so with that example in mind, I'd like you to complete the remaining Lewis structures independently. And if you need additional reference examples in terms of drawing Lewis structures and predicting electron pair and molecular geometry, I would encourage you to reference the lecture videos provided in Canvas. So once you have filled out all of your report sheets, again, you'll be submitting your full report in Canvas into the Laboratory 5 report submission page. Again, you'd open the assignment and you'd upload either a photo, video, Word, JPEG, or PDF document into the following upload link, and then you'll submit your report via Canvas. Wonderful. So that concludes the full walkthrough for Chem 100 Laboratory 5, and we'll discuss the next laboratory experiment in a future video.